Hi everyone. Today we're going to jump in and we're going to work through some trigonometric applications. And so if we can bring back kind of all of our skills with all of our trigonometric functions, I think we should be good for today. The goal today then is to give a context to some stuff and to be able to kind of put everything together. So what you'll see on the screen, there's our first problem that we're going to walk through. And what I want to do is I want to hit out maybe some key components and some things that we can consider in this application. So pause the video, give it a full read. Okay, we should be back. So as you take a look, that graph is going to represent that motion in front of a motion detector. So I'm just going to go through and I'm going to highlight a couple key things on the graph that are going to help us to be able to go through and answer kind of some circumstances about the problem. The first thing I think we should notice is that the middle of my graph, and no, that's not an asymptote I'm putting on the graph, but just to kind of recognize that the middle of that graph seems to represent 8 meters. We notice that the bottom of that graph has a value of 2, and the top of that graph has a value of 14. Now, we can also tell when that top and that bottom occur. As you look at the bottom, I can faintly see some grid lines in there. So I kind of have a 1, a 2, a 3, and a 4. So each one of those grid lines is worth 1 unit. So at 1 second, that minimum occurs, and at 3 seconds, that maximum occurs. So I have some key components that happen on that graph. Now, if I was starting to then put it into some context, let's take a look at the first problem. The first problem says, what is the equation of the axis? So let's answer that first part of the question, and you can see that highlighted as the middle line on that graph. So the equation of my axis would be y equals 8 on a generic graph. However, because the problem is talking about distance versus time, we probably wouldn't use y to represent that. We'd maybe use d. So d equals 8 would be the equation of the axis. And what does it represent in this situation? So we could clearly give a context and say that it represents halfway in between. However, can we actually start to kind of think about the context a little bit? What we have in the situation is Michelle swinging back and forth in front of a motion detector. And so what that means then is at that first starting point, Michelle is 8 meters from the motion detector. She then swings and is 2 meters away from the motion detector. She continues to swing and then is 14 meters from the motion detector. That we start to now have context to it. And so what does that 8 represent in this problem then? Yes, we could write that it is halfway, but that's really just stating again what the equation of the axis is. Instead, when we take a look at it, let's think about that context. If it represents halfway, then it's not dealing with the motion towards and the motion away, that would actually represent the resting position of Michelle. That once Michelle stops swinging, she's going to lie 8 meters away. Now, we could also make a note that the equation of the axis, because it's 8, would represent the starting position, but we have to be very careful though. Don't make a comment about the starting position, because it could have been quite easy that Michelle started swinging at another distance. Okay, let's take a look at B. What is the amplitude of the function? Well, the amplitude we can pretty easily calculate. We see that we have a maximum of 14, a minimum of 2, and so therefore my amplitude has to be half of that height, which would be 6. Question C, what is the period of the function and what does it represent? Well, for us, that period of the function, we notice that we have a minimum at 1 second and then a maximum at 3 seconds. And so we know then that the distance between those, the min to the max, would be 2 seconds. We know that that equals half the period. And so we can see that we have a period of 4. Now, we do get a little confirmation on our graph. If I was to trace over one cycle, then we could look down on that graph and see that that takes 4 seconds. What does it represent in this context? We should be good in this context to say that that represents the time to complete one full, and I don't know if we want to use the term like swing. That is the time for Michelle to complete one full swing and get back to her starting position. Okay, let's jump in and deal with a few more situations in this context. Okay, so as you take a look at the problem, I've now thrown on application like D, E, and F for us to work through. So we should be able to go through pretty quickly and answer D and E. How close did Michelle get to that motion detector? Then that's a case where we're looking for the minimum distance, and it's 2, and we're talking about meters in this context. How far from the motion detector was Michelle at 7 seconds? So if I was to come over here and look at 7 seconds, I'm looking at that value, and we should be good to be able to go through and say 14 meters. We actually have some confirmation, though, that if we know that she hit her max at 3 and the period is 4 seconds, then that means she has to also be at her maximum distance at 7 seconds. Now we come to question F, and I just want to scroll up a little bit so that we can take a look at what F asks us. If the motion detector was activated as soon as Michelle started to swing from at rest, how would the graph change? And this is where we have to kind of get to an understanding a little bit that as we look at some of these trigonometric applications, we should be able to recognize that maybe there are moments where something looks like a trig curve, but it doesn't have to always exist as that trig curve. And so if I had to give you a situation, let's take a look at the actual graph. So we're looking at that picture, the actual graph of Michelle swinging. And I want you to imagine how consistent Michelle must be to always be swinging that way. That her action to swing towards the motion detector and back away and towards was consistent every time. Notice, she always got to 2 meters and she always got away 14 meters. That's incredibly consistent. The other part being she does it in exactly the same amount of time every time. That full swing takes 4 seconds, never changing, is remarkable. So what I'm trying to get at then is, notice Michelle was always swinging, even from the very beginning. So I want you to think and imagine that maybe we're on a swing set and you're going to start to swing as you go. What would it look like? Would it look like Michelle's graph? And maybe we might be able to say, well, If I did have my vertical axis, which was my distance axis, and I had my horizontal axis, which was my time axis, that if I started to swing on that swing set, yes, I can get up to a graph that looks pretty much like Michelle's. However, for me to start, if I start at resting position and now I begin to swing, I might swing a little bit closer, and then I go a little bit farther away, and a little bit closer, and a little bit farther away, and a little bit closer, and a little bit. That then only at a certain point, maybe am I hitting my 2 meters, and now I'm somewhat consistent. The other issue could be that maybe like Michelle wasn't that good at getting her momentum going right off the bat. And so perhaps this was her swing at the very beginning. Short, now all of a sudden she hits that stride. So notice the period, the length of time it takes to complete a swing may be very short early on. And now she hits this window where it matches the graph above. The last part could be, like, keep in mind that I could have changed it. Maybe she kicks back first and then starts swinging towards and now hits. So we have all these different things. And the biggest issue, I hope, is that we can see that, no, like, Michelle swinging on that swing is not periodic all the time. But maybe there are parts to which her motion would be periodic. Maybe there is a time period where it would be periodic for a few seconds. So as we start to take a look at some of our trigonometric behavior, or periodic behavior, what we want to do is maybe recognize that we do have maybe some moments where that graph may not be periodic, or we have moments where the graph is periodic. What we're going to examine are the moments where it is. Okay, let's jump into some other applications. So now what I'd like you to do is just pause the video and give problem 2 a read. And I'd like you to give problem 2 a full read, all the way down to part C. Okay, we're back. So I want you to take a look at A, because we're going to walk through A together. What I'm asking you to do is to sketch a graph of the height at time t after the tire picks up the nail. So the first thing that I would hope we would be comfortable with is we're talking about a first quadrant graph. We'd find it very difficult to deal with negative time, especially since the problem says after picking up the nail. But also, we're dealing with height always being positive. At the very least, that tire goes down, or the height of the nail, I should say, goes down to ground level. Okay, the question then says, sketch the graph of it. So now we're going to put on the graph of what happens as that nail rotates on that tire. So the key thing is sometimes we'll get people who will want to draw a circle because they're trying to picture physically, like there's the nail, and the nail then will go around. We just have to be careful with that. So if we were to take a look at that and imagine that my tire was going this way, what we would then end up having is the height of the tire starts to increase. It's then going to increase up to its maximum. The height then decreases, and then it returns all the way down to the ground. And so if we were to start with that, we pick up the nail on ground level, the height of the nail increases. Now, I just want you to notice why that's a curve and why it's not linear. Is that if we go and examine on that wheel, you'll notice that as we move from the bottom of our graph, just let's say to that height, as our time continues, so let's even just think about slope, that I get a little bit of raise in that time. So it takes me a little bit to get there for a tiny raise. As I start to get closer to the side of the tire, now only a little time has to go by to get a lot of raise. And so only a little bit of time gets me a lot of increase in height. And so we'll see that we have that curvature to that graph. So what I'm going to do is I'm just going to erase all of that so we can produce a nice picture. There's my h-axis, my t-axis, and I'm beginning to draw my graph with that increase. Now my my nail gets all the way to the top of the tire. It's then going to decrease, and it then returns to the ground. There is a graph of the height of the nail above the ground at time t in seconds after picking up the nail. So I'm just going to get rid of my tire picture. And there we go. Now, my recommendation to you is that graph could represent anything to anybody right now. We need to put some details on our graph. And so if you can go through and label a maximum value, a minimum value. Notice, I'm only talking about the value to those. That's all. And then put on your period. Then you have everything you need to be able to build the equation of your graph, to be able to talk about the context of that graph, to give your reader the meaning to the situation. Some people like to put on one other piece of information, and they like to put on a starting value. Only because it helps them, and in some cases, they would like to put on a middle value. You can put those on if you wish, but I'm telling you, if you label the red, you're good. So, what I want everybody to do is pause the video now, and I want you to try to label those 3 properties on your graph. Go to it. Okay, we're back. So the first thing we should notice is the tire's diameter of the car is 52. So we start then at a minimum of 0 because the nail's on the ground. That's how it gets picked up. And then we get to a maximum of 52. It says the tire picks up the nail and it takes 6 full seconds for the nail to complete a revolution. And so my period down here is going to be 6 seconds. There we go. If you have that red drawing fully labeled on that blue set of axes, you have everything you need. Okay, some people are going to like to put on the other values. Well, we already have our starting value on at 0. So to put on my middle value, I would have to be exactly between 0 and 52. That puts me at 26, and we're talking about centimeters. Some people are going to like to put on the green. You may like it. So now what we're going to do is just get rid of all those properties on the right. Because what I want to do now is to take a look at problem B. How high above the ground is the nail at 7 seconds? So the first thing we can see is that it's going to be outside that first cycle. So if I was to continue my graph, and I can as my tire spins and so on, I would know that my 7 seconds would exist somewhere around here. So we can see then that my answer to that question should be a pretty small value. But we can actually get to a more concrete answer on that. If we know that 26 goes all the way down the middle of that graph. And this would represent like a trigonometric function. It looks like a trig curve. Then I know that every one of my trig curves can be broken into quarters. I'm going to highlight on my first cycle. There is my first quarter, then my second quarter, then my third quarter, then my fourth quarter. And we know that in each one of those quarters, we go from a minimum to a zero to a max to a zero. And so I know then that when I get to this point in the middle of my graph, that has to take a quarter of my period. And so if 6 seconds is a full rotation, then 1/4 of that would be 1.5 seconds. So I know the location of that point would be at 1.526. I know I would then get to my max at half my period. I know I would then get to my middle again at 4.5 seconds. And then I get to my minimum. And so if I was to continue, I know that I would get back to that max another 1.5 seconds, so at 7.5 seconds. And so therefore, I know that my answer to question B has to be somewhere. If I had to say my height, I know it's got to be greater than 6, but it's got to be less than 26. That would be my estimation. Okay, we're going to need to get a more exact answer than that. And so because it doesn't land on one of those quarters, those maximum, minimum, or zero values, we're going to need to come up with the equation that would represent that curve. Okay, I'm going to just go through and get rid of all of that purple now, because I want to make sure that we're good, that we don't think we need the purple to build the equation of the graph. I told you, as long as you have your max, your min, and your zero labeled, you are good. Okay, let's build the equation. So, we're good that back a few lessons ago, we were able to work our way through and build the equation to a function. That you could build your sine or cos, whatever you wanted to, if it took this form. And so what we can do then is we can go through, and if we can find all the components in that equation, we can build the equation. So I'd like everybody to take a moment and try to build the equation to that graph. Pause the video now. Okay, we're back. So the first thing that I think we should do is we could nail out some key properties to that graph. We should be good that that graph has an amplitude of 26, half the height. And we should be good that the middle of our graph, so therefore the equation of our axis, would be at 26. Okay, we need to come up with our period. And I said a while ago that we really want to have this relationship in our back pocket, that our period is equal to 360 over k. We talked a little bit about what we can do in a situation and how we can work with that context. I want to make sure that we're good because we can see something in practice right now. Okay, the first thing that we should notice is we found that the period was 6 seconds. So, if I was to substitute in my 6 seconds, I'm just going to put all my units back in there. And I know I give you guys grief for putting units in a math equation. That's a science thing. But I think it's going to help us to see one big concept now. Back on the canned word problems day, we talked about a conversion factor. And maybe we'll be able to see it here. That if I solve for k, I'm going to have 6 seconds times k equals 360 degrees. And then I divide out my 6 seconds. that when I calculate my value, 360 divided by 6, I get 60. But when I put my units in, I'll notice that that would be degrees per second. And so when I find that K value is going to be a way that we can now substitute in and convert all of our units into degrees. So when you solve for that K value, you're finding two things. You're finding the way to stretch your function horizontally so that it fits the correct curvature. It repeats the way it should. But you're also finding a way to change the degrees into other units. Okay, so let's build the equation then. Well, the first thing is I should be able to go through and fill in a bunch of details. I've got my equals, my amplitude was 26. I haven't decided sine or cos yet. I know that I have a K value of 60. I don't have my variable, but I know that I have a D value of 26. Okay, the next most common things. Notice we don't have a function that is y and x. Look at your graph, look at the situation in A. We are talking about a function of height that is made up of time. The next thing, and if I just went now and slid some of that stuff over to be able to make a little bit of room. We now have to make a decision on what type of curve do we want, a sine or a cos curve. And if you recall back, my decision on sine or cos can help me because then I might not have to deal with a phase shift. And as you take a look at this graph, because our starting point is at the minimum, then I think I know what I want to use. For me to go through and build a height curve, I am going to use a negative cos graph. If I reflect my cos curve that normally starts at the top across the x-axis, it will now start at the bottom. There is the equation to my function. So make a couple key notes. You have the proper variables in there, h and t. We've now determined a good starting point. We've stretched it to have the proper amplitude. We have stretched it to have the proper period. And we have shifted it up to have the proper middle. There's the equation to your graph. Now that you have that, it should be really easy for us to be able to work our way through. To answer that question, we're going to sub in t equals 7. Remember, our expectation, we should be getting an answer somewhere between 0 and 26. So when we make that substitution, and I'm just going to clear out a bunch of that purple work on the side to make some room, then we should be okay to come in on negative 26 cos 420 plus 26. Now, okay, we can push buttons on that as we work our way through. However, we should note that you could also come up with the value of 420 on your own. You know a full rotation is going to be 360. So that means that we go another 60 degrees into our first quadrant. And your special angles are going to tell you that that is a root 3, 1, 2 triangle. And therefore, the cos value would be adjacent over hypotenuse. And now we can calculate that, and we get a negative 13 plus 26, and we get 13. Put on your units, we're talking about meters, and you are good. There we go. Okay, so what I'd like you to do then, work your way through C. Okay, so we're back. So the only reason I threw in C is I could have everybody right now, and probably your instinct was then let's just sub 15 back into that function. However, I do want to maybe get to a point where we might be able to simplify some things for us. The reason I say that is because when you go and you build that equation now, you're going to have to calculate 60 times 15. So we're going to get to our 900. And yes, I understand that in a situation like this where you're going to push buttons, having a number like cos 900 isn't really an issue. However, what if we asked you to come up with an exact value and you couldn't use your calculator? You would then have to go off, as we did before, and deal with rotation angles. And so now you're going to have to go through and say, okay, well, how much are we rotating for? Okay, so 360, 720. Okay, 720. So there's a 1.8. And then you would have to go through that process. And my guess is that after we have to go through and complete multiple rotations, you might prefer to try to work in a context where you only ever had to deal with one rotation. So what I want to do is I want to take a look back up at B, and I want us to notice something. That this action of subbing in t equals 7 was not needed. And I'm hoping that some of you could have seen that we could have subbed in t equals 1 and got the exact same answer. That this action of going 1 second into that next rotation is the same action as going 1 second into the first rotation. And by doing that, I don't have to deal with multiple rotations. And so when I look at subbing t equals 15 in, my other option could have been this. Well, let's take 15 seconds and let's divide it by 6 seconds. Because that 6 seconds is my period. So then what I want to do is I want to change that into a mixed number. And if I now divide out that 6 into that 15, it goes in 2 full times. What that's telling me then is that I have 1, 2 full rotations. And then what I would have left over is 3 out of 6. Now I'd like you to notice I didn't even reduce the 3 over 6 because I don't really want to reduce it. That 3 over 6 tells me that I have to go 3 seconds into the next rotation. 3 out of the 6 seconds. Which means that really all I needed was 3 seconds into the first rotation. And so my action of subbing in t equals 15 would have been the exact same action as subbing in t equals 3. That way I always ensure that I'm working within one rotation, and coming up with those trig values may be easier. In either case, you have an algebraic way in question C to work your way through it, or you can see that we actually get to the maximum at that value. And your answer then would be 52 centimeters. Oops, and that should have been centimeters here. Okay, not too bad for us walking through that first application. Let's try one more. So what I'd like you to do is to give this problem a read, and then I want you to try it on your own. So when we pause the video this time, I want you to go start to finish. Within question A, let's go ahead and let's build our graph. If you can produce a sketch, have those 3 things labeled on it, max, min, and period, then I'd like you to be able to go through and try to complete problem A, writing the equation that represents that situation. Okay, let's pause the video now. Okay, we should be back. So, you've given the problem a read. You notice that we're talking about a Ferris wheel. So, that Ferris wheel has a diameter of 18 and travels at 2 revolutions per minute. So, what we're talking about then is our height versus time. It tells me that at the bottom of the ride, the passenger is 2 meters. I really hope that when we went through to build our graph, our initial sketch looked something like this. You have to be very careful. Our starting point should be here. I don't know very many Ferris wheels where you start your ride at the top and then go down, or start your ride in the middle somewhere. We start that ride at the bottom and then we increase. So to go through and label those properties, my bottom should be at 2 meters. We could label the top up here at 20 meters. And you have your period. It says it does 2 revolutions every minute. My guess is, for most of us then, we turn that into 30 seconds. Be very careful. We don't want to label our period as 0.5. Not because there's anything wrong with that, but in the question, it told us that t is defined in seconds. So I want to write my period in seconds as opposed to saying 0.5 minutes. Okay, now that we have those properties, we should be good, and we should be okay to go through and build the equation. So as I go through to build, a couple key things that I'm finding. I notice my amplitude is going to be 9. My height is 18, amplitude's half that. I notice that my period being 30 seconds means 30 seconds has to equal 360 over k. I'm going to go back to being a math student now and forget about my units. I've got 360 over 30, and so when I divide that out, I got 12. Now, the last part, and this is the part that most people struggle with, is that we have to be careful when we're talking about our vertical shift, and I'll label that with our D. Remember, your vertical shift, how far the graph moves up, but it also represents the equation of your axis. And so if we wanted the middle of that graph, I would have to go my amplitude up from the bottom or down from the top. And we should see that if I move 9 up from the bottom or 9 down from the top, we get to a middle of 11. And there's my D value. So my equation then in this context, I'm talking about height. What do I want to use as a curve? Well, my curve's starting on the bottom again, so I would like to use a reflected cos graph. I have an amplitude of 9. By using my reflected cos graph, I don't have to worry about a phase shift. Now what I need to make sure I do is stretch it properly and now shift it up to the middle. And there's the equation of our curve. If you have that, then we should be able to jump into B. What I'd like you to do when you play around with B, first I want you to estimate your answer, have an idea of what it should work out to be, and then let's go through and let's find that exact value. So pause the video now, give it a shot. Okay, we're back. So everybody knows that they can go through and they can sub in t equals 20 for that value. And therefore, there's us working our way through. Now, my estimation. If 30 seconds takes my full period, then I know that half of that has to be at 15 seconds. I know that a quarter of that, I'm just going to put that line down, would have to be 7.5 seconds on either direction. So 22.5 seconds. So if this graph was talking about finding a point at 20 seconds, then I'm looking for somewhere in there, which puts my height somewhere between the middle of 11 and somewhere below the max of 20. Because it's only 2.5 seconds, like I'm probably looking for something just a little bit greater than 11. Okay, so we're working our way through. Now, I understand that the question says, how high is the passenger above? That means we can get an approximate that you're probably pushing buttons on this. However, if it did ask for exact, then maybe I can't push buttons, so I'm going to go through and deal with my cos 240. 240 puts me down here somewhere. 60-degree angle into quadrant 3. That means that my adjacent side, or opposite side, adjacent side, and hypotenuse. For me to deal with my cos, then I'm talking about adjacent over hypotenuse. And so if I calculate that, then I have my 4.5 or my 9/2 plus 11, and that's going to get me to 15.5, and we're talking about meters. There we go. So hopefully not too bad. Your job then is to make sure you're good with trig applications. Our first example today gave us something to be able to just kind of break down a trig curve to talk about certain applications, properties for that. Our last two examples show you the importance of being able to build the equation when given a graph. If you can build the equation, even when you have a pretty crude sketch, then that gives you the ability to be able to go through and find anything you need. Okay, your job, jump in and get some practice. Best of luck.